Hello and welcome to part 4 of our group Titan project overview. And this is for Computer Science 471 at California State University, Fullerton. My name is Alex. And we're going to be going over our fourth assignment, which was doing live capture using Wireshark of a TCP transfer between our computer to a remote server. So to demonstrate this, I have Wireshark open, and we're going to, let me go ahead and just start a new packet capture. So we're going to start that, and let me just get rid of these HTTP. There we go, so we can see everything. So now what I'm going to do is I'm going to navigate to this website, and I'm going to retrieve a copy of this. So I've already done that. And let me actually find it here. Let me see if I can grab it really fast for you. Let's go to, sorry, desktop's a bit of a mess. There we go. So I have it right here. It is under 7.4, right here, alice.txt. And what we're going to do is we're going to upload this to a remote server. And oh shoot, sorry, let me go back here, sign in, and let's try that again. So we're going to upload this to a server contained here. So we're going to choose our file, and we're going to choose the alice.txt, and keep in mind we still have Wireshark running in the background. And we're going to go ahead and open it. And we're going to upload. Congratulations, we have uploaded a copy of the TXT file onto their server. So now let's go ahead and stop Wireshark and let us take a look at all of the TCP messages that were there. Oops. That's not correct. It's all lowercase. Okay, so let's see if we can find it here. Actually, let me go to analysis. I'm gonna go to enabled protocols, and I'm gonna just disable HTTP so we can just concentrate on the TCP stream. And we're gonna just go ahead and find our transfers here. There we go. So the green is where it starts of our actual upload. So essentially the assignment was just to answer some questions about, it always does that, to answer some questions about this TCP session. So let's go ahead and just review some of those answers and just take a look at how we actually do that in Wireshark and what the implications are. So the sequence number of our TCP SYN segment that's actually used to initiate the TCP can actually be viewed right here. And it's this right here. It's this first SYN statement. And the way we know that it is actually a SYN statement, besides the fact that it says that right here in the info field, is that we can actually look at the TCP protocol, the actual segment itself. So when we're looking at it, we can see the length of the header, which is 28 bytes. We can see that there is a flags field within the header. It's designated as a SYN, and we can see why that is. It's because I think that's the 10th bit is set to 1. Or excuse me, that's the 11th bit set to 1, so designating that as a SYN. And also gives you some other information, says that it's over port 80, says it's chat level security, and gives you the initial window size. Well, this is the initial window size for the handshake. So, and as you can also see, is because of this initial SYN statement, it's given us some other information as well. It's given us sequence number that has the initial window size. Actually, I'm sorry, I'm looking at the wrong message here. There we go. So this is a sequence number of the initial handshake. It gives us the initial window size, and it gives us our MSS, which is our maximum segment size. And this is how many bytes can be sent in a single packet as advertised by my computer. So as you can see, it's going over port 13959 to port 80. So this is my computer talking to their computer. And then port 80 sends a response saying with a SYN-ACK. So you can also see that's a SYN-ACK in the flags field from the TCP header. And again, it's just ones in certain bit positions to designate it as a SYN-ACK, and that's an acknowledgement of the initial synchronization. And as you can see, the website that I uploaded to has responded with an acknowledgement number that is actually incremented from the sequence number of the initiating SYN statement. So see how my the sequence number of the initiating SYN statement ends with a 3393. We can see that the response of the SYN-ACK sent back to my computer is responding with 3394, essentially starting the session, the TCP transfer session. And we can see that their computer has advertised a window size of 14,600 bytes. And that is the maximum window that our computer, or excuse me, that my computer can, or excuse me, that's the maximum size that their computer will send information to my computer. And as you can see, the segment size is 1460. And then we have a series of ACK statements. And it looks like there's also some other traffic going on here, but for the most part, you can see the length here, 470, 1460, 736. It looks like it actually had lost connection at one point. I had to resend, it looks like. And yeah, I keep sending everything 1460 right here. So this is just a steady TCP stream with packets being sent containing the maximum amount of data that was advertised by their web server. And every time you see, oh yeah, look at that. It looks like it changed the initial the number here. Oh wait, no, it's the same one, excuse me. So every time you see the 13,960 to 80, that's my computer sending a message to their web server saying, hey, send me more data, or hey, this is how much data I've received so far. And then every time you see 80 to 13,960, that's them saying, hey, this is how much we're going to send. This is the maximum amount of data that we're going to send you. This is like the largest window to expect. And so as you can see, as the connection goes on, the window sizes actually tend to increase. So with the minimum window size actually being established right here in the SYN-ACK, it's actually 14,600. But as you can see, as our TCP session continues, you don't see a number that low anymore in the window size. You see it being around either 16,000 or something more than that. So that essentially implies that they, in order for in order to prevent TCP congestion, they're kind of the server that I'm uploading to is kind of lowballing how much space they have allocated for receiving data. But after the handshake and as the connection continues, the window size continuously increases, showing that the connection is good and we don't have to worry about TCP congestion because there's a good connection, and so it's allowing for a larger window size. And yeah, and as it progresses, we can see that, you know, for example, in this frame 1125, it's they are responding to. Let's see if I can find it here. So this is actually the frame that I'm looking at, 1125, is actually responding to the segment which is in frame 1111. So not the immediate, not the frame that was immediately before it, but is actually the one that's all the way up here. And so yeah, so just this whole analysis basically demonstrates how TCP works. That it's not just a single continuous stream of data, as a lot of people may think it is, but it's actually a series of back and forth communication between the host computer and the web server. So again, this is the TCP conversation between my computer and the web server as I'm uploading data to their server. So as you can see, it's quite involved, and you can actually see the dialogue between my computer and the web server. It's quite interesting. And then after everything is said and done, you can see the FINAC statement, which is actually the statement, the request to close the connection, and that is sent by the receiving machine. So essentially this is saying, oh, we've received all the data that you've advertised that you're sending, go ahead and close the connection. And then my computer is sending an ACK saying, okay, no problem, I will close the connection. And then the connection closed. So yeah, in essence, that's what's going on with TCP. And I just want to double check if there's anything here I missed. We can look at how long it took for this whole process to happen from the very first SYN-ACK to the last one. So as you can see, at 66.34, this is in seconds, at 66 seconds, 0.34 is when it started, and at 88.85 is when it ended. So it's about 22 seconds, give or take. So that's total amount of time for this conversation to happen, for me to send a file over, and the dialogue that happens between my computer and theirs. And yeah, and as I already said, this is TCP conversation, and this was our assignment 4, implications. As far as TCP, if you can if you can facilitate how the TCP works, like if you actually get into the protocols, or if you get into the TCP protocol itself and write your transferring algorithm to change TCP, maybe you can just ignore the ACKs and just keep sending without constantly asking the receiving server if they've received everything. Just keep sending it and sending it and sending it. That's one example. Another example could be instead of even establishing like a certain window size, maybe you can completely just say, hey, we'll send the whole thing at one time. Or conversely, from the receiving end side, you can actually throttle the connection by only receiving a window size that's maybe much smaller than this, to prevent web traffic from rendering your system slow or anything like that. So yeah, that's our TCP conversation, TCP stream. And actually, we can also take the time right now to just look at another feature of Wireshark, which is our TCP stream graph. And we can look at it. It's a time sequence graph. For this sequence, oh wait, that's not the right sequence. Let's try it with this one. It should show a stream graph of the actual dialogue between the two. And yeah, it doesn't look like we're going to get it. Okay, so actually I can bring up another example. I'll just show you the one that I was assigned. So this assignment actually included a Wireshark file, trace file, and their connection looked more like this. So mine, not so much. It's kind of sparse compared to this. But you can see, according to their this is the exact same process, sending a file over or uploading a file into a remote server. You can see that they're uploading in packets of, looks like 6 or 7 packets at a time, but it's happening every like 0.2 seconds. So you have this consistent stream of 6 packets every 0.2 seconds, and the reason for that could be a number of things. it could be something from it could be their institution router only allowing them to send so much data over so long. But obviously we didn't have that problem here with our connection. It's very sparse on our end here. But that's a basic TCP conversation that we can observe using Wireshark. And thank you again for tuning in, and we'll see you next time.